Hello, everyone. I know that sponsored talks are usually kind of boring, and a lot of the time it just feels like a big ad. So I've tried my very best to make it not a sponsored talk, including not using our corporate slide template. So it's going to look a bit wacky, and you can enjoy that. Thank you so much for attending. I'm actually glad that all the people that were here earlier have mostly cleared off, because that was just really daunting. But I'm looking forward to sharing some really cool stuff with you today, some things we've been doing with Rust, some things that some friends of mine built, and I'm going to show it off and take the credit for it, and it's going to be just a wonderful time. So my name is Kailan Blanks, and I am part of the developer experience team at Fastly. I've been working there for about 5 years now. And in that time, I spent a lot of time working on examples to really get people excited about using our platform. And as well as that, just getting the existing customers to understand how to do it. It's not always straightforward. We took a really big bet with the introduction of WebAssembly as the core component of our compute platform. So making sure that the customers can understand how to use it was really important. It's certainly been a challenge, but we've had some great results from it. So today I'm going to talk about specifically using Rust at the edge. Clicky click, no clicker today, never mind then. So let's talk about the traditional approach that we would take when deploying software. Specifically, I'm going to be imagining that I'm deploying some kind of full stack web application, maybe written in JavaScript, because that's what everyone seems to do nowadays. You would have your code layered on top of a server process. Now, your code may have vulnerabilities. The server process, Node.js, may also have vulnerabilities. And then on top of that, you're sticking it on top of an operating system, which is usually running within another operating system under a hypervisor or a container engine. And there are just so many places where things can go wrong, and there are so many things that you need to think about. On top of that, you have the actual bare metal as well, which majority of us hopefully don't deal with nowadays, unless you're doing embedded Rust, which is fun. But most of this has been abstracted away. But the core thing that we want as developers is just to be able to run our code somewhere. And that's where we come into the way that we do things today for the majority of us who are lucky to work in forward-thinking companies. That's a serverless cloud platform. A lot of the time, all of these things are done the exact same way by the exact same people for their entire engineering career. Unfortunately, there will be slight changes in the way that things happen. You might be preferring one operating system at one company and another at your next. And keeping on top of all of the different dependencies and areas where things can go wrong is exhausting. And it doesn't give you enough time to actually just focus on writing good code. So where do you put a serverless cloud platform? Now, I hate this term along with a lot of other people because it's not serverless. There is a server there. We all know there's a server there. But from the perspective of a developer, there is no server. But where does that actually exist in the process of your users making a request to your application? Well, in order to make a request to the application has to be packaged in some way to run on a serverless platform. And there are 3 ways that that's happening right now. In order of popularity, I would say the first one is Node.js, which is built on the V8 JavaScript engine, which is a JavaScript engine that was built for browsers. Now, that's not necessarily a bad thing, but it has been co-opted to run server-side. And that tends to come at the expense of resources, whether that be CPU or memory. I mean, we all know how much memory Chrome uses. So then there's another option that we can consider that has just as good a developer experience, if not better. This is containers, where you can run pretty much any code you want, any program that you can run on a normal operating system, you can run inside of a container. But it takes longer to start a container than a Node.js runtime instance. And you are going to be sharing that instance across multiple requests and multiple users. So if your program or a dependency that your program is using has a memory leak vulnerability, which we've all seen many times across the web, that's going to impact you. You have multiple requests going to the same instance. And it's kind of weird saying that like it's a bad thing, because that is how things have been for such a long time. Like we're all just used to, you have a server running a process and every request goes through that same process. But it doesn't actually have to be that way, because there's another option, which is WebAssembly. WebAssembly is really exciting. And I mean, originally it was for the browser. Does anyone actually know about running WebAssembly outside of the browser? Just a show of hands, anyone? 1, 2, there's a few, okay. So it's a relatively new idea, but you've probably all seen the WebAssembly demos where there's a native application compiled to run in your browser. One of my favorites is Audacity. I use Audacity here and there when I have to randomly edit some WAV files. And someone compiled it to WASM, and it just, you go to audacity.io or something, and it's just in your browser. You don't have to bother around with downloading it. It's really cool. But what if you could do that on the server side? You can't run code in the browser that needs to perform some kind of privileged operation or have access to a database, because of course, anyone is then going to be able to get that permission. You also want your code to be written in the language that you prefer, or that your team prefers, or that it's cheapest to hire engineers for. So it's great to be able to also just not worry about that. And also, Node.js and V8 are dominant in the industry. You do have SpiderMonkey as well, which is used by the Firefox browser, but actually the majority of people are using V8. And when it comes to containers, the majority of people are using Docker. But with WebAssembly, there are actually multiple open source compilers and runtimes that are all equally as good, and they all have their benefits. But the biggest benefit is it's not one organization controlling the whole thing. So it's a pretty safe bet to work with that technology. So where do we run our WebAssembly? At the edge. Does anyone know where the edge is? Anyone want to take a guess? I'm genuinely curious. Where is the edge? Everywhere. That's a good way to put it. Anyone else? No? Everywhere was the answer that I was hoping for. But the truth is that everyone has a different concept of where the edge is. I Googled it because I don't know. I wanted to know, where is the edge? And apparently the edge is an observation deck located in New York City. I don't think that this was a really helpful answer, because an observation deck is the last thing I want to put Rust near. But it did get me thinking that maybe it is a physical location. Where in the world does the edge exist? Is it here? Is it here in the brewery in London? Is it on each of our mobile devices or laptops where we're browsing the web? Or is it maybe part of the Wi-Fi network? Or maybe it's down the road a bit at Telehouse in Docklands. It's a big data center, but it's still kind of located within a metro area. It's very close to us. You could feasibly put things there that are privileged while still having your data elsewhere. Because the last thing you want to do is have every single request from your users travel across the globe to US East 2 or US East 1 in AWS. It's not the best experience. Of course, transiting the globe for every request is not worth it. So in my opinion, the edge lies somewhere in the middle. And I've put together a little graph to demonstrate that. In an ideal situation, the edge, where you run code at the edge, is between your origin, which is where your data is stored, and your end users, but close enough to your end users that you're not transiting the internet for as much as possible. You want it to be close so that they get a low latency response. You want it to be close so that your application is available globally and you have an even experience for all of your users. So many times someone sticks a little project on a VPS in US East 1 and it gets overwhelmed, not just because people are browsing it from all across the globe, but because they haven't thought about scalability. But the edge is everywhere. In the example I showed, that data center, Telehouse, that's not just the edge. That is a part of the edge. The edge is closest to you. It's wherever you can access it. Who uses it? Who built the edge? Well, this is one of my favorite examples. I don't know how old this picture is, but one of the first times I heard about the edge was from Netflix. And they built these lovely red boxes that they call an Open Connect appliance. And they would send these out to ISPs all across the world to put inside their exchanges and data centers. And the idea is this is Netflix in a box. It syncs all of the most popular content from Netflix. They even had some algorithms that would just send the content that's most popular in the region that that box is serving. And it means that the internet's backbone is not getting clogged up with streaming the same Netflix series again and again and again for potentially millions of viewers. And this really worked for them. It allowed them to scale massively. It was advantageous for them because it reduced their bandwidth costs and improved the performance for their users. It was advantageous for the ISPs because they're sending less traffic over their backbones. It was just a win-win situation. And as a user, it was pretty great too. There's a reason why Netflix had the best streaming experience for a long time. But that's only possible at the scale and economies of Netflix. What if you want to build the edge yourself? Well, that's exactly what my company did, Fastly. We built an edge, and this is an example of one of our POPs. POP is a point of presence, fancy word for a data center. And we put a bunch of POPs in different locations all across the world where we figured that we could reach users as efficiently as possible. But we're still talking about a company. As a person, you want to be able to just deploy your code to the edge. And that's why our abstraction over this is you're going to see something more like this, where you can deploy your code and see metrics. And that is exactly what I'm going to show you how to do now. So we're going to do a little bit of live coding. It's going to be really basic. I'm just going to deploy a really simple Rust application to the edge. And then after that, we're going to go right to the opposite end of the spectrum, and I'm going to show you a really complex app written in Rust at the edge, which I'm going to hope works the first time that I show it. And it will really give you some inspiration of how powerful the web can be when you can move it closer to your users. So let's have a look. So the very first thing I'm going to do is start a new tab in my terminal. I'm going to make it nice and big so that everyone can see, ideally. Is that good? Show of hands. Yeah, good, perfect. OK, so let's make a new directory, and we're going to call it my edge app. And inside of my edge app, we're going to run fastly compute init. And we will accept all the default parameters because that's what we want. Of course, we're going to choose Rust. It would be quite embarrassing to build a JavaScript project at Rust Nation. And we'll go with the empty starter because I really just want to show you the basics. Fire up your editor of choice, and once again, make it nice and big. So we've got a really simple directory structure here. You're all familiar with the source folder and the target folder and cargo toml. Hopefully not familiar with fastly toml yet. We've added this extra file in here called fastly.toml, and this just gives our tooling some idea of how to build your project. And inside the main file, we have a macro that allows you to write a main function with a different signature than you'll be used to. This takes in a request, which is simply an HTTP request, and it returns a result with either a response or an error. Really basic stuff. In fact, let's add some string here just so we can see what's going on. And we're going to go ahead and deploy that. Why did they add this comments tab? It's just not necessary. So we'll run fastly compute publish now, and that's going to build our application. Not only that, it will notice that we don't have a service configured, and it will ask us if we want to configure one. There we go. We'll create a new service. We'll again go with the defaults. We'll choose the funky domain that it has generated for us. And we don't want any backends. I'll go into what these are a bit later. So while that's deploying to the edge, which can take a little while because it is deploying to every single Fastly POP around the world, I just wanted to talk a bit about why WebAssembly was the right choice for this. It is because of our vision of the great future of edge computing, where we have multiple components building a service rather than just one binary. And that will allow you to mix the best of the Rust ecosystem with the JavaScript ecosystem, with the Go ecosystem, because something we find the most is, unfortunately, Big company engineers just want to write JavaScript. It's what they're used to, but unfortunately, it isn't the most performant option out there if you're really trying to work at scale. So for those operations that take a bit longer or require more processing power, it's really great to be able to step down into Rust or perhaps even C if you're feeling it, and process data and send it back to the JavaScript application. And WebAssembly components are the way that we see that working. You'll essentially be able to define an interface between different components, and you can link them either at build time or runtime. So in an ideal world, you'd be able to just swap out one component for another without affecting any traffic. We're not quite there yet, but in the meantime, this is what we've got. So the application has been deployed. I'm going to open it in my browser, and surprise, surprise, hello world. Woo! Okay, thanks for coming to my talk. No, I'm joking, of course. So if we refresh the page, we'll see that we're getting responses between 11 milliseconds, which is great, and 213 milliseconds, which isn't great, but I'm going to put that down to the fact we're on conference Wi-Fi. But the fact is this response that we got in 11 milliseconds, in that 11 milliseconds, we not only made a request to a server somewhere in London, but that server spun up a brand new WebAssembly instance, ran this code, and returned the result. What that means is this request is entirely isolated from any other requests, which has huge security benefits. And it still includes that amazing sub 150 microsecond startup time that I mentioned earlier. That is the core of our edge compute platform. It's a really simple example, but let's maybe look at something a bit more complex. And that is machine learning. We are going to be showing you a machine learning implementation of a recommender engine. And a recommender engine is something we're going to be used to all over the web. I'm going to pull up an example of one now, and I'm taking a huge risk here showing you my Amazon account. Let's hope there's nothing embarrassing. But we all see this every day and don't really think much of it, but there's a huge amount of data science happening behind the scenes to serve us this page. There are a whole bunch of categories of recommendations here, and I just want to explore a few of them and just consider how they're built. So there's pick up where you left off, which in my head is a really simple one. It's you view these pages, you might want to go back to them. You don't need any kind of data science there. You just store a list of what they viewed and serve it back to them. And I imagine keep shopping for, buy again, and continue shopping deals are largely the same. This will be an intersection of that data set where those items now have deals. These will just be ones where you have already purchased but are likely to purchase again. What else have we got? So this is a bit more complex. This is gift ideas inspired by your shopping history. So these aren't necessarily items that I viewed, but it's looked at properties of the items that I have viewed and try to find other items with similar properties. Now that's pretty impressive. What's this? Calling all 18 to 22-year-olds. Well, I never gave them my date of birth, so they've just made a wild assumption there. That, again, is less interesting. But I think the one that I really want to focus on here is gifts inspired by your shopping history. How could we implement that ourselves? Well, if I was building an e-commerce website, I would probably find some kind of server out there that is designed for this. I'm sure there are solutions where you can just feed it a bunch of different documents and it will be able to find correlations between them. But that has to run on a server somewhere, probably is a long-running process. That server needs to scale to all of our users. And it also needs to be quite widely accessible. You don't want again, to make a request halfway across the world in order to get the recommendations. You want your shopping homepage to load immediately because it's been proven that that increases the conversions when it comes to sales. So how could we do that at the edge? And specifically, how could we do that at the edge with Rust? Well, I'm going to introduce you to a project by some good friends of mine, which is a recommendation system built on Fastly Compute. And it's really interesting, actually. I'm going to show you the site that we're basing it off of first. This is the New York Met Museum, which if you haven't visited, you definitely should. It's an incredible place. But they do something really interesting, which is that all of the art items and objects that they have, which is hundreds of thousands, are all cataloged on their website. And this is great because if you see something that you like when you're there, you can find out all about it. You can find the origin, find out what it was made of. But, you know, if I viewed a whole bunch, I'm kind of curious to know like what else I might like. Related artworks is useful, but actually maybe I have a thing where I really like oil on canvas, and perhaps the site could see all of those different interests and recommend me items. So how can we go about enhancing this website at the edge to add that functionality? Well, the first thing is we need to know all of this information, and scraping it is an option, but that's actually not necessary because the Met has a fantastic data set of all of the items on their website, and it's here in this GitHub repository called Open Access. To be fair, it hasn't been updated for 2 years, and I imagine they've had more items since then. So maybe not the best example, but you get a huge CSV with hundreds of thousands of items. And I'm going to show you what that looks like now. I've actually opened it already because opening this in the Numbers app takes about 10 minutes. It's a huge file. But it has all sorts of interesting parameters for each item. So of course you've got to have an object number. This is just the identifier within their system. You get the title, the kind of things you'd expect to see. But then you have columns within a data set that I've never seen in my life. I mean, I don't think I've ever seen a spreadsheet with dynasty and reign. So that's really interesting. And there's another great one here. What is it? It's medium. So you can see what it was made of. And that's quite useful. But there's a ton of data here, and this is a really great resource to build a recommendation engine from. So how can we make use of this at the edge? I don't think that loading all of this data into memory and making operations on it is a good idea. First of all, it's going to take way too long. If I couldn't open this on my fancy MacBook, I doubt we're going to do that on a little edge server. But also, it's just not the most efficient way. There are way better ways to do this. So let's take a look at some ways that we can pre-process this data to make it manageable at the edge. I'm just going to open up this document now. So the first step is to pre-process the documents. And what we're doing here is taking every single item within that data set, and we're just concatenating different parts of it into one long description line. This makes it a lot easier for us to manage later. So let's take a look at an example of this. We've gone from that big CSV to just a line for each one that is the title, type, artist, medium, date. And we can be fairly sure that that information is available for all of them. From there, we're going to run a Rust application. Now, it's worth mentioning this is not a Rust application running at the edge. This is a Rust application that is designed to run on our machines beforehand, or perhaps run in CI and pre-process the data to be ready for the edge. And what it's doing here is a whole bunch of fancy maths. It's taking information from those descriptions, which have been computed into vectors. If you're not familiar, vectors are just a way to represent that kind of data numerically, and you can use vectors to determine the distance between two items. If two items have a small distance, then it's likely that they have a lot of similar properties. If it's a large distance, probably not. That's a great basis for a recommendation engine. So this is just taking all of that computed data and packaging it in using the bin code crate, which is ideal because we're going to be deserializing the data using Rust. We may as well use a Rust-focused encoding. And not just that, it's going to write it out to a whole bunch of files, lots and lots of files, which end up being right here. There are, I believe, 500 in total. And these all contain grouped items. It contains a bunch of items that are similar to each other, but each file will still be processed afterwards. We'll go into that a bit more. So let's get to the exciting part, which is the Edge Recommender application. So the first thing I want to do is actually just show you what it looks like to to experience this website with the recommendations. So I have a deployed version of the application here, and I'm going to go to one of the product pages, item pages. It's a hat. But we will see as we scroll down a whole bunch of other artworks matching your interests, powered by Fastly. And the way that this is working is when we load the page, we are making a request to the recommend endpoint. And the reason that that endpoint is being called is because we have injected some JavaScript into the page somewhere here, right here. This is because Compute is very good at processing responses and modifying them. We take the request from the client, and if it doesn't match any of the special routes that we've written, it's going to proxy that request to the Met's website. So we're going to just do some validation. We're going to get the response from the Met website as if the user had just browsed to it directly. We'll make some changes to any URLs that are present on the page in order to make sure that when people click links, they're not sent back to the Met. They stay on our proxied version of the website. And then finally, we stream the body to the client and inject our HTML right at the end. And that injected HTML is the CSS and the JavaScript for the things that we are implementing. The JavaScript is relatively simple. It is just looking to see if we are on an object page, and if so, it makes a request to the recommend endpoint. If it gets objects back, it's going to request the details of all of those objects, and then it's just going to inject all of those all of the data onto the page underneath the existing related artwork section. But the meat of what's happening here is in the serve recommendations method. So we have a module here called recommender KV. The reason we have that is because before we had a KV store product, we had a different way of loading this data into memory, but we've recently been able to make it a lot more efficient. This is going to load the database of vectors from the Fastly key value store, and then it's going to compute the median vector for the IDs that were passed into it. The IDs that were passed into it are the IDs of the items that the user has recently viewed. So if I look at the request that was made for this page, you see that we have made a request to recommend, and we've passed it only one ID because that is the ID of the item we're viewing. But had I been browsing the website, there would be a whole list there. Because there's just the one, it's just going to find items that are similar to this one. And the way that it does that is computing the median vector between all of the IDs that we've provided. This provides a good representation of what the user is interested in. And then we search for the specific cluster, which, if you remember, are these files here, which contains that item. Once we've loaded that, we can build a special kind of map that will allow us to search that cluster with finer detail and get information about the items that the user is most likely to be interested in. Now, this is all pretty computationally expensive. This is something that, again, you would usually be doing on a single server as part of your e-commerce solution. But what we've done here is just added it on top of an existing website. And not just that, it's really fast. I mean, I refresh the page and that comes up almost immediately. The actual recommendation isn't taking long at all. The bulk of what's happening here is actually fetching the item details. If we had access to the Met's database of items, we would be able to pull that in a lot quicker. But you can see here, recommendation is taking about 35 to 34 milliseconds, well within the range of what we would expect for an e-commerce website. And we've done this without working with the Met as well. We just took their website, proxied it, added some functionality, and this is something that anyone can do. And it doesn't require any scaling. If 500,000 people went to this page right now, it's going to run absolutely fine. I might get my account suspended because I think I have a billing limit somewhere, but you could absolutely just scale this up as you scale up. If you suddenly get a surge of users, it's not going to cause you any headaches, as long as your backend can manage serving the actual pages themselves. But we can go in and actually reduce the load on the Mets backend as well. And that's exactly what we've done when we load the object details. We're setting a TTL on the request. And what that means is when the Met responds to us with the details of an object, Fastly is going to cache that for this period of time. So any further requests coming in aren't going to go to the origin. They're going to be served to the user instantly. And that's why the page is loading so quickly. So the code for this is available on GitHub. It's available on the Edge ML Recommender repository under the Fastly organization. And I haven't seen any customers doing this yet, but it's a possibility, and it's something that someone just wanted to try to do, and they were able to do it at the edge without spending thousands on bespoke infrastructure for recommendations. And it's just inspiring, really, that you don't need to think about how it's being deployed. I deployed this to the service that you're seeing by running Fastly Compute Publish. It's that simple. This is a new way to write Rust. There are a few caveats. You won't be able to use crates that are depending on system calls that aren't available in the WebAssembly environment. Currently, you can't read from the file system, but that's okay because we have stand-ins for that. We have the KV store, which is exactly how we're loading in all of these objects here. And because we have these bespoke methods for pulling in data, we can make them really performant and we can suit them to our network. So actually, when the service is pulling in all of these precompiled clusters, it's going to be pulling them in from hardware within the same building rather than from wherever your application was deployed. And that's really, really helpful. That is all I have today in terms of code to show you. What I did want to do is give you one more demo. And this is something that we're showing off at our booth over in the room where you get your food and your coffees. And it is another really powerful example of code running at the edge. It is not Rust, because Doom was not written in Rust. But this is the original Doom codebase compiled to WebAssembly running at the edge. Now, I'm sure you've all seen Doom running on your browser. I've seen it running on a pregnancy test, I think. Someone managed to make that work. But this is the game running in the browser. But it's not. If I inspect and look at the network tab, what you're going to see is a whole bunch of requests. A whole bunch of requests. And every single request here is a frame of the game. The service running this is completely stateless. With every request being sent, we are sending the entire game state as a payload, and we're receiving back the rendered frame as well as the next state of the game. So there is nothing being stored on the server side between each request. And as I mentioned earlier, every single request is going through a brand new WebAssembly instance. There is no shared memory between any of these frames. Not just that, I'm on conference Wi-Fi right now, and it is perfectly payable. So just another example of what the Edge can do. And if you want to give that a try, you can look for it on the Fastly documentation site or come by our booth where we have a couple of computers running it. And we'd definitely be happy to chat to you a bit more about the Edge and WebAssembly and anything, and the weird recommendations on my Amazon. That is all I have. I have a link here for anyone interested in the WebAssembly system interface. This is the future of the component model that I mentioned. This is going to be a standardized interface. As you saw earlier, we had a special Fastly macro in order to invoke the request response cycle, but this is something that is being standardized, and as soon as that is ready to adopt, we're going to be supporting that. We're really standards first. We're actually a founding member of the Bytecode Alliance, who are building the WebAssembly engine that we use, and we really want to just make this something that can be used all across the web. We don't like vendor lock-in, and we're working really hard to make sure that WebAssembly is usable by everyone. That's all. I would love to take questions if anyone has any. Sure. Do we have a mic? Thank you. I should have warned you.
Hey, thanks for the presentation. Really enjoyed it. I'm just curious how you, I didn't understand the part where you kind of proxied the Met website and then injected your own recommendations into it. I think you went through that a little quickly. So if you could just explain that again?
Yeah, absolutely. I'll go back to it actually in order to show you. So the core method that I showed you earlier, the main function, it takes in a request and it will return a response. But you don't have to construct that response. You could forward that request on to another server and then get the response back and do something with it. So you can call request.send met, and you would define met as a backend here in your configuration. The reason we do that is because we're very security first, and we want to ensure that requests are only going out to origins that you control and you want requests to go to. There is functionality within the SDKs as well to build these backends dynamically, but we recommend, unless you need to do that, to find them manually. But when you send the request, what you get back is a response object. Now we could take that response object and we could just send it back to the client like so. And what we've built right now is a really simple reverse proxy. It is just going to forward all requests to the origin, forward the responses back, and not do anything to them. But of course, now we do have a response object here, so we can do what we want to it. We can take the body and manipulate it, and then put the body back in the response and send it to the client. So does that explain it a bit better? Yeah. Great. Yes, that's exactly what we're doing here. We're sending the request to Met Web backend, and when we receive the response, we're not only changing headers in the response, but also taking the body and injecting something at the end of it. Thank you.
Yep.
One at the front here. Oh, one back there afterwards as well. Hello.
Quite a lot of efficiency is gained from having long-running processes and where they can like share state between different requests by different users. How are you like fixing that like loss of efficiency from having to like spin it up and down every single for each request?
Yeah, that's a good question. So there are kind of two answers there. So the thing you mentioned about spinning up and down for every request, what we do is we spin up the application or service, as we call it, once at build time, and then we take a snapshot of that state. And then when we create a new instance, we use that existing snapshot. So there is no initialization to happen, really, apart from just copying what's already there into another part of memory. In terms of the benefits of shared state between different requests in long-running processes, that is why we have our caching APIs. So you can cache any kind of data and then retrieve it from any other requests, and that will stay within the POP that you're in. So it's a very low latency request. If you want to be keeping state globally, we have solutions like the KV store, which allows you to read and write, which is eventually consistent globally. And then if it's to the point where you need something that it has strong consistency guarantees, that's when we would recommend that you make a request to your backend and do it there. Not everything is suitable to run at the edge.
Thanks for your talk. I was wondering how you are moving the files to the KV. Is it also in the TOML file or something?
Yeah, that's a really good question. I did skip over that. Let's have a look. So let's take a look at this one. There is a script called upload to KV store, and it just runs a command that is in our CLI, which allows you to create a KV store entry by passing in a directory. And when you do that, it will add entries to the KV store where the key is the path of the file and the value is the contents of the file.
All right, thank you. And you were mentioning backends. Would you, if you need a database, for example, is that something you would host somewhere else and then configure as a backend, or?
Yeah, absolutely. If you need to speak to external services, then you would create a backend. For some languages, we support that kind of happening magically as long as you permit it. So an example of that is JavaScript. If you have a JavaScript library dependency that is making a request somewhere using, say, the fetch API, you can't tell that library to use the Fastly fetch API instead and pass in a backend. So we have a flag that will allow you to dynamically create backends on the fly as they're requested by these libraries. That isn't feasible with Rust yet because there is no standard library for making HTTP requests. Once the WASI HTTP spec that I was talking about is finalized and implemented, then you would be able to just use the WASI HTTP library, and any other cloud provider offering this kind of service, it should just work without any fuss.
All right, thank you.
I think there's one just further back there.
Yeah.
Thank you. I should have asked everyone to move forward.
Yeah, thank you. How does it work when you're using WebAssembly to run all of this? How is the isolation? I guess you're running many of these requests in one server. Which is the isolation layer between different requests? How do you ensure that a malicious code that's uploaded cannot interfere with another one?
Yeah, that's a good question. So WebAssembly, I want to be accurate about this. I would say that WebAssembly by design is isolated. Every WebAssembly instance that you run has its own memory space. That memory is not shared unless you explicitly choose to share it. So yes, you could spin up one WebAssembly instance and then call the request handler multiple times and have the same instance process it. But you can also really cheaply clone the WebAssembly instances. So like I mentioned, we have a pre-initialized state and we just copy that to a new point in memory and run the code there. And then we tell the runtime that it can throw away that memory and reuse it for a further instantiation.
And I guess all of this is handled by the runtime that's interpreting the WebAssembly code.
Exactly, yeah. And the runtime that we use and build is open source as well. It's called WASM-Time. So you can run this all on your machine as well.
Okay, so it's relying on the correctness of the runtime.
That's right, yeah. The runtime is also audited by external consultancies, as well as being open source, which generally is a security win.
Perfect.
Thank you. Hi. You mentioned the KV store is global and eventually consistent. So I was wondering how long does it take for it to be eventually consistent across all the points of presence?
It's a really good question, and I don't know, but I'm going to showcase the power of our documentation and find the answer right now. It'll be embarrassing if it's not here. The data in our data stores is globally available, durable, eventually consistent, and is read-write both at the edge and via the Fastly API. Read latency is typically under a millisecond, but maybe up to 300 milliseconds. For data that has recently changed or is not yet replicated to the local POP.
Okay.
300 milliseconds.
Cool. Thank you.
Hey, thanks for the talk. Do you have any numbers around how much you're saving on network latency? For example, for a request going to the edge compared to going to the US from here or China or wherever?
Yeah, that's a good question. I mean, I don't have numbers on me that I could share. I'm certain that we have some blog posts that would have numbers. It really depends on the individual implementation. We have a lot of customers, not a lot. We have some customers that will put Fastly in front of their services and not configure it any further than the defaults. And there is some improvement, but the difference between that and a company that has the engineering resources to really figure out how Fastly works and optimize it to their needs will see much better results. I think it's worth mentioning as well that there's not just a latency benefit, performance benefit, but there's a big cost benefit as well, because if we are caching the content in our POPs, you are having less requests go to your origin. That's lower egress costs, as well as the cost of having engineers on call because things keep crashing whenever it gets busy. But yeah, to sum it up, I would say we have that information online. I don't have it to hand, unfortunately.
yeah, it'd be a good like motivation to sort of sell this to your organization, you know, to have these kind of network benefits and so on.
Yeah, absolutely. We actually started as a CDN company as well. For many, many years, we just offered kind of CDN services that were highly configurable, and that was a huge selling point for us. You know, customers were able to get much better cache hit ratio because they could configure fastly to work in the way that their services need. It wasn't until 5 years ago that we started saying, okay, well, you can't just put configuration at the edge. You can actually just fully write code. And I foresee a future where it's just code at the edge because it was so straightforward to get that Rust application running that proxies the requests. Thank you. There's one more here at the front.
Yeah, thank you. There's in the example you showed, you're doing request back to the origin, and I guess that request is actually something that you have to wait for. So you could potentially be doing many requests concurrently. Is that currently possible, or are you waiting for?
That is possible, yeah. So the request.send method that I showed you is blocking, but there's also a send async method, which is non-blocking. So you can wait for that request to come back and then you know, do other stuff in the meantime. You could also fire off 20 requests and start sending the first one as soon as the response is received, or you could wait for them all to come in. You can do standard async programming.
So all of that is built on top of WASI, because I understand that async is coming with WASI previous 3, right?
Yeah, so it's not true async, as in, that there aren't multiple threads. But what we can do is we can keep track of multiple requests from a runtime perspective. So you can send a bunch of requests and then poll to see when they have returned, or you could use a helper method to block until all of them have returned. So you can't use kind of async await as it currently exists in the Rust ecosystem, but that is a future goal as well. As you said, it's part of the WASI spec.
Thank you.
Okay, well, if there are no more questions, I'll give you a bit of time back. I'm a little bit early, but that's fine by me because it means that we can all have a little rest and a coffee before the next sessions. Thank you so much for your time. If you'd like to speak more, please come to the Fastly booth. We'd love to have a chat with you and maybe get you signed up for a free developer account as well, because we're giving away prizes for people that sign up. Thank you very much.